This lesson is about geometric annuity. So, recently we've been studying arithmetic annuity, in which the consecutive payments have a common difference. In geometric annuity, the consecutive payments have a common ratio. So, to be more specific, consider an n-year annual annuity immediate with first payment X and each subsequent payment being 1 plus K times the previous payment. So the present value of this annuity is X times 1 minus 1 plus K over 1 plus I power N over I minus K. If I is not equal to K, but if I is equal to K, then the present value is nx over 1 plus I. So I is the interest rate, whereas k is the growth rate of the annuity. So if the interest rate and the growth rates are equal, then we have this second formula. Otherwise, it's the first formula. So if instead of annuity immediate, it was annuity due, which means the first payment happens right now, then it would be the same formula as 123.1, but multiplied with 1 plus I. So this one gets multiplied with 1 plus I. And when the second one gets multiplied by 1 plus I, the 1 plus I in the bottom cancels out, and we just get nx. Now, if instead of annuities, we have perpetuities, then the present value of geometric perpetuity immediate would be x over I minus k, and that of geometric perpetuity due would be x times 1 plus I over I minus k. And in both these cases, I needs to be bigger than k. Now, if the interest rate and the growth rate are equal, then it doesn't make any sense for to talk about the present value. Similarly, if the interest rate is less than the growth rate, then also it doesn't make any sense, because in both cases the present value would blow up to infinity. So the geometric perpetuity formulas only hold when the interest rate is greater than the growth rate. So let's look at an example. First payment of a 5-year monthly annuity is 200, happening 1 month from now, and each subsequent payment is 5% larger than the previous one. Find the present value of the annuity. The annual effective interest rate is 6%. So each payment is a certain percentage larger than the previous. That means it's a geometric annuity. And since the first payment is happening 1 month from now, so it's a geometric annuity immediate. And the payments are monthly, so we will need the monthly effective rate. First payment is X, which is 200, and the growth rate is denoted by K in the formulas that we had. So in this case, K is 0.05 because each payment is 5% larger than the previous. And since the payments are monthly, so we need to figure out how many months we have. It's a 5-year annuity. In 5 years, there are 60 months. And we need the monthly effective rate, let it be J. So 1 plus I 12 by 12 power 12 equals 1 plus I, where I is the annual effective rate. And the I 12 by 12 is the monthly effective rate. So 1 plus J power 12 is 1.06 because the annual effective is 6%. So J comes out to be 0.0048655. And now we can use 123.1 because that's for the present value of a geometric annuity immediate. So x times 1 minus 1 plus k over 1 plus I power n over I minus k. So in this case, it's the J that we're going to use, which is a monthly effective. And the first payment, which is X, is 200. 1 minus 1 plus the growth rate was 5%, and the monthly effective was the 0.00486755, and N was 60 because there were 60 monthly payments over J minus K, and that comes out to be 57423. And in the choices we had, that was choice D. Second example, first payment of a 5-year annual annuity due is 200, happening 1 year from now, and each subsequent payment is 6% larger than the previous one. Find the present value of this annuity if the annual effective is 6%. So this seems very similar to the previous one, but the important difference is that now the growth rate is also 6% and the interest rate is also 6%. So that's I is equal to K situation. We will use the second formula over here, nx over 1 plus I. So n is again 60 because no, in this case, it's a yearly payment, so it's a 5-year payment, so n is 5. So nx over 1 plus I, n is 5, and x is, again, 200. That's the first payment over 1 plus 0.06, so that's 943. And then the next example, the first payment of an annual perpetuity due is 300. And each subsequent payment is 4% larger than the previous one. Find the perpetuity value at time 9 at annual effective 6%. So the interest rate and growth rates are different. And then it's perpetuity due. And so we look at the perpetuity formulas. It would be this one. So x times 1 plus I over I minus k. So x is 300 in this case. I is 6%, so 300 times 1 plus 0.06 over I minus k, 0.06 minus 0.04. Remember, the geometric perpetuities make sense only when I is bigger than k. Otherwise, the values blow up to infinity. So the present value is 15,900, but we don't need the present value. We need the value at time 9. So once we have the present value, we can always push it forward to time 9 by multiplying it by 1 plus I power 9. So multiply this 15,900 by 1.06 power 9. That's 26863.